Hey, what's up, guys? So I'm going to go over this problem from discussion worksheet number 4, I believe. I think it was number 5. This tablecloth problem, only because I think it's probably the most complicated of all of them, and the forces and their directions get a little bit confusing, especially the friction ones. So up here I've actually written out some helpful, I guess, forces to think about whenever doing these problems, and I've also divided them into the two common categories, the long-range forces, the case where objects don't have to necessarily touch, but they still have a force acting on them. And the only one in this class that we're going to care about is gravity, so I've written it there. And then, and in this particular case, the two types of forces that we care about are so-called normal forces and so-called friction forces. The reason I have them in quotation marks is because I want this video to make sense no matter what point in the class you're at. So if you're watching it at the time that I upload this, you guys probably haven't learned technically what normal forces are and the different types of frictional forces. And at the time of that worksheet, you guys also hadn't learned any of those. You guys hadn't learned them formally. So nonetheless, let's just jump right into this problem. I've kind of drawn this setup. I found this picture online. I believe this is the last lecture article on the Daily Bruin. But anyway, so we have this case of Josh pulling the tablecloth to the left, and there's this plate on top. Okay, and you guys have all seen this, like magic, not really magic tricks, but those. If you pull it really, really fast, this thing will stay put. It'll slightly move forward, but for the most part, it'll stay put. And the idea is, let's try to analyze the different forces acting on all of these objects. And in this problem, which is why it's so hard, he had you identify all of the forces on all three of these objects, right? So that's where it got kind of confusing. But let's start off from the top down. Okay, so let's start off with the plate. Let's ask ourselves, for the plate, what forces are acting on the plate? Well, I think the easiest one always is pretty obvious. It's always gravity. Anything on Earth is going to feel the effect of gravity, so we have gravity's force acting down. And I always write F for force and then sub G for gravity, so the force of gravity. Then what else do we have? We have this interaction with the tablecloth, okay? And this is the trickiest part. So I'm going to leave that frictional force, that's kind of making it shift left and right potentially. I'm going to leave that till the end. What other forces do we know are acting on it? Well, let's think about all the different. Let's go through it systematically. Let's think about all the objects that are interacting with it. We already got rid of the long-range forces, so now let's think about the contact forces. So the only object that this plate seems to be in direct contact with is this tablecloth, and that tablecloth is exerting a couple forces. The first one is probably the most intuitive. It's keeping this plate up, right? I mean, otherwise the plate would be falling down. And some of you might be thinking that the table is keeping the plate up. And in some philosophical way, you're right. I mean, the table is keeping the tablecloth up, and the tablecloth is keeping the plate up. But technically, the tablecloth is what's keeping the plate up. So for this one, I'm going to draw a force up with the same length, actually, this is kind of important, as the force of gravity, because it's not moving. So these forces have to cancel out, right? To where if you were to add these two forces up, you would have essentially no force in the up and down direction. And that makes sense, because this plate is not moving in the up and down direction. If anything, it might slide in this problem, but it's not going up and down. So I'm going to call this the force of cloth on plate. Now let's ask ourselves, this is where it gets hard. If I were to pull this tablecloth really, really fast, okay, or really, really slowly, it doesn't really matter. But if I'm pulling this tablecloth to the left, or if Josh is pulling it to the left, what direction, if it's going slowly, let's say, do you expect this plate to go? I assume your intuition tells you that this plate is going to move to the left, right? Just going to kind of like follow if you go really slowly, it's just going to follow the tablecloth. If you go really fast, it might stay there, but it might slightly go forward, but the tablecloth will be pulled out by the time it falls off, but it might shift forward a little bit, like I don't know. Let's see if I can use some skills here. You might do this, right? If you were to pull it really fast, the tablecloth might be gone, but this might go like here. So it's going to move to the left in some way, shape, or form, or it's just going to be dragged to the left. Either way, it's going to the left. That was a very long-winded way of saying that plate is probably going to go to the left even a little bit. And in that case, we have to have some force that's making it move to the left, right? If you like zoom out and just look at it in the real world, that thing is going to the left, there must be some force. So that force is probably going to be some sort of frictional force between the tablecloth and the plate. So we're actually going to have some sort of frictional force, friction from the cloth. Right? So this is, again, it's probably a little bit confusing, but it really helps to ask yourself that fundamental question. What direction is this plate going to move? And why? Why did it move in that direction? Well, there must have been some force acting in that direction. I know it's a very intuitive way of thinking about it and not a very mathematical one, but I think it really helps for this problem. Okay? And now I'm actually going to skip over to... Actually, let's go ahead and go straight to the tablecloth. So for the tablecloth, I'm going to go over here. For the tablecloth, let's ask ourselves what forces are acting on it, and this one's going to have quite a few. So let's get ready for this one. Again, first we have gravity. That one is always there. Now let's think about what other objects it's interacting with. Well, let's go with one of the trickiest ones first. Josh. Josh is pulling the tablecloth to the left, so we have some sort of force that's going to the left. Now let's call that force of pull from Josh. Okay, so that's that. We got those two down. Now let's think about some other forces. What else is this tablecloth interacting with? Well, it actually happens to be interacting with both the plate and the table. So let's think about the two easy forces, I guess, quote unquote easy forces that are being exerted by those two objects. Well, they're pushing on the tablecloth, right? Both up and down from both the objects. So the plate is actually pushing it down. Force of push from the plate, and the table's pushing it up. The table's pushing it up. Let's write table. Force of table on cloth. All right, so we already have four forces, but let's also keep something in mind. I'm gonna try and put this in the most intuitive way to really make it sink in. What is the only reason you might have any struggle at all pulling that tablecloth? So imagine if this table was gone, if that plate was gone, and you had just a snapshot moment where this thing was like floating in the air, and you were to pull it to the left. Would that be easier or harder than if it was sandwiched between these two things? Well, it would obviously be easier, right? If you were just pulling it without anything touching it, it would be easier. So why is it harder? Well, the reason why it's harder is because we have some force going to the right that's opposing this pulling force, right? Let's make them smaller just to keep it in scale. And this is actually going to be the frictional force. Frictional force from, let's say, the plate. And this one's going to be the same thing. Some frictional force from the table in this case, right? So again, these are very, very unmathematical, non-detailed ways of thinking about it. But I really want you guys to ask yourselves, why are things moving the way that they are? So why is this tablecloth harder to pull when it's being touched by these two things? Well, that's because there's a frictional force being exerted from those two objects, the plate and the table respectively, onto that tablecloth in the opposite direction that you're pulling. And likewise, that same reasoning applied to this plate. Why was it moving to the left? Well, there must have been some force in that direction, making it go to the left. Things have to move with forces. Okay, and again, you guys might not have learned this, you may or may not have learned this by the time you're watching this video, but if you think of Newton's third laws, you can actually think of this force and this force being a Newton third law pair, where the frictional force from the tablecloth onto the plate is equal and opposite in magnitude to the frictional force of the plate onto the tablecloth. If that was confusing, then you might not have gotten there yet to Newton's third law, but if you have and you're watching this video, that should make sense and come together nicely. And lastly, let's think about the table. Let's think about the table here. Let's think about the table. What forces are acting on this table? So let's ask ourselves. The table, again, always has the force of gravity. That one's easy. I'm always going to add that in there. It's pretty simple. Now, ask yourself this other question. Given the Newton's third law pair, right, we know that this frictional force from the table is making this tablecloth harder to pull, right? So we can already kind of, if we know Newton's third law, kind of intuitively think that this tablecloth, that this table has a frictional force, friction from cloth, that's going to the left. But that argument, given Newton's third law, might not be convincing enough. So let's think about something else. Let's ask ourselves, if this table was super slippery, if this floor, if the ground that this table is on was super duper slippery, what do you expect would happen if you tried pulling this? Think about a real world situation where if you were to try pulling it. Wouldn't this table kind of slide over to the left if the ground was like super slippery or full of oil and you tried pulling this? Wouldn't this entire table move to the left? I'm trying to erase. I'm still getting used to this app. But yeah, it would, right? This table would slide over to the left. And that's because there's some frictional force from the tablecloth onto the table that's going to the left. Okay? So I think that intuitive argument is probably the most convincing as to what's going on. So let me just move this over real quick. Give ourselves some more room. Okay, so let's think about what other forces are acting on it. Let's think about some other trickier forces, I guess. Firstly, the tablecloth is sitting on top of that table, and we have a similar quote-unquote normal force. You guys may or may not have heard of that term, but some sort of pushing force, right? This thing's resting on this table and it's pushing it down, right? It's in contact with it. So we actually have some normal force here. Force of cloth onto table, right? So the cloth is both like sort of pushing down the table and also, you know, causing some friction on the table whenever it's being pulled to the left, right? So we have these two forces. Now, let's think about what other forces are acting on it. We have this ground over here touching it, right? In this case, it isn't really touching it. We have a really poor leg. Well, let's say we have this ground over here touching it. This is causing what kind of a force onto the table? Well, it's causing a pushing force going up. So we have some pushing force going up. So force of ground on table. And these two should be equal in magnitude to an extent, right? Well, that was technically not true because we have to also incorporate the gravity. So this arrow going up has to be equal to both of these arrows going down. So if I want to be technically correct, let me erase this just to be precise. And erase this as well. These should be about, I don't know, two smaller arrows such that when you add them up it equals this arrow over here. But let's ask ourselves, when we pull that table to the left, we're pretty confident in the real world this table is not going to move. And the question is, why not? Right? We only seem to have one arrow going to the left, so we would argue that the table has to move. It's only one arrow, it's only one force going to the left. But if we think about the other interactions that are happening between the ground and the table, we can also include some sort of frictional force. And the term that we would use in this one, if the table doesn't move, is a static friction. But the technical name isn't really that important for this video. The more important thing is that we have to know that there's something that exists in the interactions involved on this table that makes it not move to the left, and that would be some sort of arrow or force going to the right that's equal and opposite to this friction from the cloth. Let's call that, friction between ground, running out of room, between ground and table. Right? So these are essentially all the forces acting on this table, on this problem. And I actually drew a little schematic down here of a zoomed in version. And if you just want to sum up the frictional forces in particular, on this tablecloth, you're going to have a force going this way from the plate onto the tablecloth, and also the same thing from the table onto the tablecloth. And for the plate, you're going to have a frictional force from the tablecloth onto the plate going in that direction, hence why it slides over at all to the left, right? And you're also going to have, let's start over here, a frictional force from the tablecloth onto the table that's going to the left. These are all the horizontal forces, I guess, going the left and right forces. I'm not going to draw the up and down forces only because they're pretty intuitive, and I don't think there needs to be much help for those. But I guess I can go ahead and label this force of cloth onto plate, and this is the force of force of cloth on the table. And this problem is genuinely completely analogous to the problem with the box on the back of a truck, or, and I believe Professor Samani went over it on Friday's lecture, when he, pulled the book and the book on top of it, pull one really quickly, one kind of moves forward, that whole thing. That's all the exact same concept as this. It's this interaction between objects. And that sums up the forces. So